Hi students, in this final video for online lecture 2, we are now going to talk about some of the atomic history and the fundamental experiments that gave us the representation of the atom. So the first one I'd like to talk about is the cathode ray tube. The cathode ray experiment was done by J.J. Thomson, and it earned him the 1906 Nobel Prize in Physics. What he determined was that a beam of particles interacts with two plates differently. It was repelled by the negative plate and attracted by the positive plate. This experiment proved that not only did the atom exist, but there was a subatomic particle that was negative. This was the idea of the electron. Now, over on the right, you will see what is commonly looked at as the first representation of what we thought of the atom. This is commonly known as the plum pudding model, but most of you don't know what plum pudding is, so let's call it the blueberry muffin model. In this model, just imagine the cake of a blueberry muffin being all positively charged, with the blueberries then being negatively charged. So using J.J. Thomson's idea, he believed that atoms were all solid mass, with the positive part being the cake and the negative part being embedded inside that massiest sea of positive. We know this to not be true, but at the time, especially in the early 1900s, and the fact that our atoms all created solid mass, this wasn't a terrible assumption to make, but we would go and make it better from here on out. For our second experiment, we are now going to talk about the oil drop experiment. In this, we are going to discuss how the measured mass of the electron was created. This was done by taking an atomizer that would go and turn a substance into fine droplets about the size of an atom, and then they would go and drop them through a small hole in which a magnetic field would then try to balance the mass of those droplets. At the same time, an X-ray would produce a charge on this droplet. So a charged species being held in suspension by a magnetic field. This ended up giving us the idea that the charge was going to be 1.60 times 10 to the negative 19th coulombs. This was different than Thomson's charge to mass that we saw back in the last experiment, but it was very important because we could also determine the mass of the electron to be 9.10 times 10 to the minus 28 grams. This experiment allowed us to now see that the electron was much smaller than we originally suspected. So now we can talk about the Rutherford gold foil experiment. This won the 1908 Nobel Prize in Chemistry and started to lead to one of the best fundamental ideas of our atom structure. What he did was take an alpha particle emitter, and he shot those alpha particles towards gold foil. Gold foil, being a solid mass, you would expect that particle beam to bounce right off of it and immediately reflect back. What Rutherford saw is it actually caused scattering. Yes, some of the beam did bounce back, but actually most of it went straight through. And in some cases, it would get scattered off to the sides, and you would see by the detector that you would get various different reflections of that energy from that gold sheet. So what does that mean? Well, now let's look at it on the microscopic view over on the right. If a beam does not hit anything, it will go straight through. But what happens if the beam just barely hits the part of an atom? It would get reflected slightly. The interesting part is because most of the beam's energy went straight through, we could now actually state that an atom is mostly empty space. So one of the cool things about this is that we now get multiple conclusions. The first conclusion is that the atom's positive charge is mostly concentrated in the middle. That differs from the plum pudding model or the blueberry muffin model because they said it was a sea of positive with the electrons scattered around. We now find that all the positive is located in the middle. This proton has the opposite charge of that of the electron. So if the electron is going to be negative, we are now going to give the same amount of charge, but opposite of that for the proton. The mass of a proton is larger than that of the electron, approximately 1,840 times that of the electron. So while we had the mass of the electron, now we end up having the mass of the proton as 1.67 times 10 to the minus 24th. So in Rutherford's gold foil experiment, there are multiple wonderful implications. The first one is we now have the nucleus. This means that the atom is mostly empty space. As the beam would hit, if it hit the nucleus, it would bounce back. If it would just brush off of the nucleus, then we would end up having it scattered a little bit to the side. If it never hit the nucleus, it would immediately go through and it would come out to the other side of the detector. This gave us the ability to not only determine the charge, but also the mass as well. So we can now come away from the plum pudding model and let's talk about the Rutherford model of the atom. So the most important taken away from his gold foil was the empty space. You can see it here. So now you see that little dot in the middle of the gray shadow. The gray shadow is empty space, but we create that shadow to show you the approximate volume that we expect atoms to have. Inside of that, in that little dot, we have both protons and neutrons. The neutron was also found by Chadwick and helps us balance the charge distribution as well as the interaction and repulsion of all that positive charge in such a small space. Now, the atomic radii is about 100 picometers. So that is 1 times 10 to the minus 10th meters. The nuclear radius is way smaller than that. So as you can see, it's about 5 times 10 to the minus 3rd picometers, or 5 times 10 to the minus 15 meters. So we're talking about 1/10,000th the size of the atom. What does that mean in relation? Well, it just so happens that if we were to be at AT&T Stadium or Dallas, or let's talk about Kyle Field right there at A&M, if the whole volume of that massive stadium were considered an atom, I could put a golf ball on the 50-yard line and that is the nucleus. So the neat part about this is all this identifying property, all of this positive charge is in such a small itty-bitty space. All that negative charge is going to be in a very large volume that is going to help us dictate a lot of the binding properties that we are going to have. So let's go ahead and summarize everything that we've seen here today. Notice that the electron is much smaller in mass than that of the proton. The neutron is of about equal mass of the proton. Notice that we have to get to the 3rd decimal place before we have a significant difference, the neutron being slightly heavier, but they're more or less a comparable mass. The electron, do notice that it is noticeably smaller. When we get to the charge, notice that the electron has a negative charge and the proton has the positive charge. The neutron is neutral. So we don't always want to remember and have to memorize the charge in coulombs. So what we're going to do is just come up with a fundamental idea and say that we're going to come up with the charge unit. The charge unit being electrons become -1 and protons become +1. The neutron staying 0. So the mass of a proton is very similar to that of the mass of a neutron, and they're both about 1,840 times that the mass of the electron. So it's important to note that the identifying feature of the atom, being the proton, is equivalent or very close to the mass of that of the neutron, but they are both much, much larger than that of the electron. So now what we're going to do is come up with an atomic mass unit. This is the mass of an atom in an atomic mass unit. The AMU is now going to be a mass unit that we get in order to now discuss stuff that is very small. By definition, one atom of carbon-12 weighs 12 AMUs. This is because it has 6 protons and 6 neutrons. So this means it has 12 total subatomic particles in the nucleus, and that is the mass that we are going to have. We do not include the mass of the electron when dealing with the atomic mass of an atom, mostly because if our electrons are 1/10,000th the mass of a proton and neutron, we aren't going to have 10,000 electrons to be able to become noticeable. So we are going to not put the mass of an electron in our calculations. So on this scale, we can have hydrogen, which just has a proton, would have a mass of 1.008 AMU. Oxygen would have a number of 16.00 AMU. The question you're probably asking yourself is, Dr. Collins, if they are all subatomic particles of protons and neutrons, where does the decimal come from? The decimal is actually going to be a weighted average of all the various isotopes, and we are going to talk about that in the next lecture. The last thing that we want to do for this is just talk about a basic fundamental ordering of our subatomic particles. This was an exam question from the fall of 2016. Order the following subatomic particles from smallest to largest in terms of mass. So if we look at these, the first answer I think you can see, because we know the electron is so much smaller than the other two, we know that A cannot be a correct answer. So let's look at B. It says the electron is much smaller than the proton, which is then equal to the neutron. Well, that seems like a pretty good answer, especially if we're talking about how close it is. So let's look at the other ones. So for C, we can have that the proton is smaller than the neutron, which is smaller than the electron. We know that that is not going to be the case. Let's look at D. I have the electron being smaller than the proton, which is then smaller than the neutron. Well, that's a pretty good answer, and especially being technically correct, D seems to be the right answer. So now if we look back at B, this is what we assume to be the case, that those masses are very close. But when we go down to the exact calculation, B is not going to be the correct answer, and we can go look at answer D. Let's just check with answer E. The neutron is less than the proton. We know that that is not the case because the neutron is the largest by mass of all the subatomic particles. So to be absolutely correct down to the decimal place, the correct answer for this question is going to be D. Answer B is a common misconception, and that's okay because most of the time we are going to deal with species and say that the proton and neutron are very close to each other. That's fine, but for the correct answer, we would want to select D. Now you've seen the importance of all the subatomic particles, and we are able to now start to build our atoms and good representations on our nuclear structure. Have a great day.